going to be the theoretical portion of our distillation and properties of alcohol lab. And so just kind of recap from Gen Chem, a boiling point we're defining as the point at which the vapor pressure of our substance becomes equal to and then greater, as we keep heating it, to the outside vapor pressure, the outside pressure in the room. And so if we have molecules that are in liquid form, remember they're condensed, they have less freedom. Remember in Gen Chem we talked about how they can take the shape of their container, but they're otherwise kind of fixed, in contrast to gases, which fill up the whole size of their container. They fill up the whole of the container, as well as take on the shape of their container. So as we keep heating our alcohols, at some point they're going to start having enough energy in the form of heat. They're going to have enough kinetic energy. Remember we talked about kinetic molecular theory in Gen Chem. They're going to have enough energy where they're going to start moving around, and they're not going to fit in, they're going to start filling up the shape of their container. And in lab, when we actually have things open and with an escape hatch, they're also going to start escaping. They're going to start moving around so much that they're going to try to fill up the entire size of the container. And if that container is the whole room, then we got our substance boiling. So kind of maybe something to review in thinking about what to make your inquiry lab on, or in how to answer some of the harder comprehension questions at the end of the lab, is just think about fundamentally what is boiling. When we were talking about kinetic molecular theory in Gen Chem, what does that actually mean? It's not just memorizing 5 key steps, but what are the molecules actually doing? Energetically, what is happening to them? So this is kind of, I have it written in one line. It's actually very difficult to think about what it actually means to have your substance start boiling. Another thing to think about are intermolecular forces. So we stressed them a little bit in Gen Chem, but boy, we really like them in organic chemistry. Talking about intermolecular forces in organic is our favorite thing to do. And so thinking about the types of intermolecular forces, well, we have van der Waals or dispersion forces, we have dipole-dipole moments right up here, and then we have hydrogen bonding as being our strongest force in organic. So if we started adding some metals, which we will once we get to enzymes, we'll get even stronger forces. But for now, kind of hydrogen bonding are the strongest forces that we're going to see for now, before we start adding metals. So looking at, I just have my bond line structures of ethanol. If it's floating around in pure ethanol, it can undergo intermolecular attractions to other ethanol molecules. In this lab, you're going to be dissolving compounds in water sometimes, so then it can also do those same interactions with water and with other ethanol molecules. So in this case, well, I have 2 lone pairs of my oxygen, and then, well, those 2 lone pairs can form a hydrogen bond with hydrogen. And then, oh, this other lone pair will form another hydrogen bond with another hydrogen. And this oxygen, well, it can also undergo hydrogen bonding. And one thing to think about in terms of these kinds of attractions are that hydrogen bonding is kind of, in this class we'll mostly see them between nitrogens and hydrogens off other molecules, or oxygens and hydrogens off other molecules. And it also helps that all of our oxygens have a negative dipole moment, and then our hydrogens are going to have a slightly positive dipole moment. And remember, this occurs when the electron cloud is unevenly shared in a covalent bond. Since oxygen is more electronegative than hydrogen, oxygen is going to be delta negative. And you can look that up at the very beginning of Timberlake when we start to talk about bonds. We have the chart with the Pauling numbers that give oxygen as being very electronegative, and then hydrogen of not being electronegative, of being actually very similar to carbon. So thinking about how attached each ethanol molecule is to other ethanol molecules, thinking about that, what might the effect on boiling point be? If every oxygen has an attraction, it's not bonded to other ethanols, but it has an attraction to other ethanols, what would the effect on boiling point be? And what if we added another OH group at the end of this guy? What would that do to the boiling point even further? So those are some things to start thinking about, and then we're going to ask you kind of what your conclusions are in the comprehension questions at the end of this lab. So recommendations for you guys, theoretically, so we're going to do kind of recommendations slash theoretical information for this lab. Do part 1 before coming into lab. That information is internet research based. You can look up, we have copies of the CRC in lab, and those are those big dictionary, encyclopedia looking manuals that have the physical properties of many, 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 many compounds. You can look at the CRC if you can't get into lab ahead of time to do part 1 and you don't have access to the CRC. You can go on the internet. ChemSpider will typically give properties of common molecules. Any chemical supply company, like last time we talked about Sigma Aldrich, Flint Scientific, if you Google, say, Sigma Aldrich, and you type in ethanol or glycerol or any of the compounds from today, they will give you their physical properties. And so if you can't get into the lab, you know, the day ahead of time to get to the CRCs, it's no problem going online. And the only thing is, if you look in outside sources outside of this class, then we also ask that you set your source. So the important thing is, as for me, if you're one of my students, I need to be able to find where you were. So if you go online to some site that isn't, it's not Timberlake and it's not our lab manual, or it's not the CRC, then just write down some website, some sort of reference, so that I know where you've been. So part 2, in this lab you're doing a solubility test, and this is very similar to the one that you did in lab number 1. So a couple of things we want to think about. If something is soluble, you won't see an interface, you won't see like kind of a dividing line in between your two liquids. If something is soluble, you'll also will just sort of see liquid. You'll see clear and colorless liquid, and it won't look hazy. So that's if something is soluble, which means that the two substances dissolve, or your solute dissolves in your solvent. You're also going to be asked to graph, and I don't care if you use Excel or Google spreadsheet, or name a spreadsheet under the sun, or if you get graphing paper, it doesn't matter to me. And if you do Google spreadsheets, you can share it to me. You can just share it to my Gmail. A couple of things to think about with graphing, though, is we want to be very systematic because this is science. And so we are going to put our independent variable, just kidding, our dependent variable up on the y-axis, and then our independent variable on our x-axis. So by independent variable, these are the things that we're varying. So if you're looking at a solubility test and you have 30% ethanol in water, and then you have 40% ethanol in water, and then let's say you have 75% ethanol in water, you're actually controlling that. Like, you have the power. You're putting the ethanol in the water and then conducting a test. And then dependent variable is whatever numbers come out of that. And so let's say you're looking at how long it takes to evaporate. So you could have different rates. Your labels might be in minutes or seconds, and then you would plot accordingly. So a couple of things to think about are whatever you are controlling in lab goes on the x-axis, so whatever you're actually putting in and you're setting up goes on the x-axis, and then whatever you're measuring as an outcome of that goes on the y-axis. Also, I want your axes labeled. On Google spreadsheets, it's kind of hard to figure out how to get the labels on, so just ask me if you have any questions. Excel, I think personally, is easier to use, but ask me questions. It could just be that I happen to like Excel a lot. So ask me questions if you don't know how to label your axes. And also, if you just have grid paper, then you can use colors, or you can distinguish your different data points in whatever way you want. So your axes should be labeled, and they should have units in them too, as appropriate. So if you just have percent, then you don't really, you don't have units. Another thing to think about is what is the easiest way to visualize the material. And the graphs, we make you do graphs, but really they're for you. They're so that you can actually see the concepts that we're looking at. So it's actually easier for you to see concepts. And so those help with your comprehension questions. With your inquiry project, actually having the graphs helps with you writing a conclusion. So you want the format of the graph to be the best so that you personally can visualize it. And normally in chemistry, we say that's a scatter plot or a line graph. Usually with bar graphs, it's not as easy to see. If, however, you're doing an inquiry project and you have a graph, and it's not as easy to see as with a line graph. If you want to do a bar graph for inquiry because that's personally easier to see, then go for it. So the graphing is for you, although there are some conventional things that we follow. So ask me if you have any questions, but normally just keep in mind independent variable on the x, dependent variable on the y, label your axes, label units as appropriate, and then make the format of the graph, so like line versus scatter, make it so that it's the easiest to see the information. Last but not least, inquiry. So with your inquiry projects, once you finish a lab, then you'll want to start making and designing an inquiry investigation with your partner. And it can be kind of a follow-up that arises out of questions that came from the lab you just did. And so typically what you want to think of is, well, what physical properties did we look at? And can I actually get measurements from them? Can I actually get numbers from them? And so physical properties that we have seen is, in this lab, with the alcohol lab, is density, solubility, volatility, so how well does something evaporate, and then boiling point. So one thing that you might want to think about is the glycerol. We didn't really examine it very much. It was just kind of, if you look at the end of the lab, after you've done the lab, you'll notice that we did look a little bit at glycerol, but we didn't really explore all of its properties and compare them to alcohol as much as we could have. So you could look at different physical properties with glycerol. Another thing is we looked at density a little bit, but is there a way that you could measure further properties of density? So maybe even, we just were looking at alcohols in this lab, maybe, alcohols versus an alkene, or alcohols versus a ketone. It doesn't, you can look at functional groups that we haven't talked about yet in class, and then find find things out on your own. That's